All right, so let's keep going with this example. So we're thinking about some little particle, a little mass on the end of a spring that's vibrating backwards and forwards in the x direction around some equilibrium point. And we said that we can use a sinusoid to describe this motion. So for our particular particle in this example, the maximum that it can move away from equilibrium is 0.11, so that's our amplitude. And the angular frequency that our particle has, which is a measure of how fast it's going, is 3.2. And if we were to plot this function x as a function of time, what we end up with is this thing that I've got down here at the bottom. So the thing to remember is that my x-axis here is actually time. So here I'm thinking about time increasing, and at each point in time I am plotting in the y direction what the x value of my function is. So just to think about what's going on here, if I imagine here is the equilibrium position of my particle, then at time t equals 0, this graph tells me that my particle is over here. Then if I look at, for example, time t equals 0.4, my particle has moved up. It's almost as far as it can get, so it's almost here. If I look at, for example, so that looks about 0.5, so at about 0.5, my particle has moved even further, and then it starts on its way back. So, for example, if I look at time t equals 0.8, then my particle will have moved back along here. At roughly time t equals 1, my little particle gets back to the equilibrium, and then it starts on its motion going in the other direction. So you can see how, off this graph, we can read where our particle is in displacement at a particular time. And that's the whole point of what we're trying to do when we're modeling things, is say, if you tell me what the time is, I can tell you where the thing is. Okay, so based on this, if we're interested in looking at a time t equals 2.4, we should, based on our graph, get something about 0.1. But let's do the maths. So let's plug this in. So we've got x at 2.4 must be equal to 0.11 times the sine of 3.2 times 2.4. And if you plug this into your calculator, you should get 0.108. So part of the reason why we're going through this is because you might not get 0.108, and that possibly means that your calculator is still thinking in degrees, not radians. So if you didn't get 0.108, please take your calculator out and make sure that it is changed from measuring angles in degrees to angles in radians. It depends on the calculator exactly how you do it, but there should be a little button that kind of says degrees to radians or radians to degrees. And once you switch your calculator on, somewhere up near the top here, you should see an R rather than a deg or a D. Okay, so please do that, because otherwise you'll get wrong answers in the exam, and that would be very sad. Okay, so we've talked about how this equation can help us find where our particle is if we know the time. But we can do more than that. We can talk about its velocity, and we can also talk about its acceleration. So to do that, we first need an equation for the velocity, which is just the first derivative of the displacement. So let's take the derivative of this equation with respect to time. So we're going to get dx by dt, and that's going to be 0.11, derivative of sine is cos. And then we need to differentiate the inner function, so we're going to get a 3.2 coming out over there. I did that very quickly. If it's feeling hazy, please go and revise your differentiation. So now if we plug in 2.4, then we get dx by dt is equal to 3.2 times 0.11 cosine of 3.2 times 2.4. And again, plug this into your calculator and you should get 0.0609. And that would be in meters per second. And I should have put meters here for our displacement. So let's just think about that. Does this intuitively make sense? Well, remember that we're looking at this time over here at 2.4. And let's think about what's happening to our particle. So it's moved from equilibrium to the right. So heading this way, and it's almost got to its furthest point. And if you think about what happens when something's on a spring, it moves quickly when it's close to equilibrium, but it moves slower the further away it gets, until eventually it stops and then it changes direction. So we would expect, as it's getting almost as far away as it can, that it would be going very slowly. And that is, in fact, the case that we see here. We've got a very slow velocity. And finally, let's have a look at its acceleration. So for this, we need the second derivative. So we can just take the derivative of our first derivative. So let's just do that. And we're going to end up with the acceleration is equal to, and you can check this, 3.2 all squared times 0.11 times the sine of 3.2 times the time. Okay, this sine is important here, and that comes out because we differentiate cosine, and the derivative of that is minus sine. All right, so if we plug in our value of 2.4 seconds, then we're going to get that at 2.4 seconds, our acceleration is minus 1.109. And again, we can do a little bit of a kind of a reality check. Does this make sense? Is it in the right direction? Well, remember, the acceleration is slowing it down. So if our particle is moving, our particle is still moving in the positive x direction because our velocity is still positive, but we know that the acceleration or the force is slowing it down, and it's slowing it down a lot, so much that it's almost stopped. So it must be that our acceleration over here must be in the opposite direction, and it must be quite big. Okay, so reality check seems to indicate that things are going pretty well with our description over here. Okay, so please do a few more examples of these, and don't just plug the numbers, but think about what the numbers actually mean. And if you do that, then you won't forget things like your units, like I just did over here. So that's meters per second squared. Okay, onward. So this might seem like an incredibly simple system that we've just described, our simple one mass on the end of a spring in one dimension. But in fact, we can use this to explain a lot of different systems that have similar principles. So what were the key things that we said about our mass on a spring? Well, we said that we have a restoring force that always pulls the motion back towards the equilibrium. And we said that the size of that force is always proportional to the distance from equilibrium. So pretty much any system which has these characteristics can be described using simple harmonic motion. So I've just used the word simple harmonic motion. That's what we call this. It's the phrase used to describe this mathematical model. And as I've said, the key thing is any situation that you find where you have a system where a restorative force is directly proportional to how far you are from equilibrium means you can use this model. Okay, so what are some of those systems? Well, simple pendulum will do it, so we're going to talk about that. You can, in fact, use the motion, you can use simple harmonic motion to understand the motion of a wheel in a car, or planetary motion, which might seem strange because you think of those as things going round. But if you're curious to see how that works, you can go and have a look at the links I put on Canvas, which will show you the link between simple harmonic motion and circular motion. There are plenty of molecular vibrations where you can actually use these models precisely to calculate how molecules are vibrating, and bunches more. I thought it would be fun for us to have a look at describing a pendulum using simple harmonic motion, because you've just been doing the experiment in the lab. So you've just been working out G based on a pendulum. Well, let's just check that we understand the physics behind those calculations. Okay, so we can consider a pendulum can be considered an oscillating body. So let's just have a nice little diagram. Here we go. So you've probably seen lots of these. Here's my pendulum. It's got a length L. I'm going to measure the angle theta from the vertical. And that's all we're going to really draw on our diagram for the moment. So we've got this pendulum and it's swinging backwards and forwards. So we can draw a free body diagram for this. So here's my little, and I've got a mass m. Here's my mass m. What are the forces acting on it? Well, we've got tension up in the string, like that, and we've got gravity acting down like that. And if you think about what happens in the motion of a pendulum, it moves along an arc like so, backwards and forwards like that. So at any particular point, we are interested in the motion perpendicular to the tension, because if you think about the motion of the pendulum, this motion is always perpendicular to the string, which is the tension. So what I'm interested in is, what is this force here? Well, that is going to be mg sine theta, because my tension is going to be all in this direction here, so the only thing that's pulling it in that direction there is the component of gravity in that direction, so that's mg sine theta. So the next thing that we're going to need to know is what usually we measure in the x direction, but that's not super helpful here because we're moving kind of in an arc. So in fact what we're going to do is we're going to measure our distance in arc length. And our arc length is given by theta times the length of our pendulum. So that you can check if you're feeling a bit rusty with your trig and stuff, but arc length, so for example this length here, is given by the change in angle over the length. And this is an important thing, this must be in radians, otherwise this equation doesn't work. Okay, so what can we do with all of this? Well, we know that the force that we're interested in, so the force acting in the direction of movement, so this is equivalent to thinking about just the force in the x direction when we were looking at our mass moving with a spring. Here we're thinking about the force acting in the direction of movement is given by minus mg sine theta, so I should have had a minus sign over there. And you might look at this and go, that's a sine, and if you think about the equation that we had for our oscillations, we didn't have a sine, we just had, so let me back up a bit and say we're used to, from what we've seen so far, thinking that simple harmonic motion happens when you have a force that is directly proportional to the displacement. But over here we've got a force that is proportional to the sine of an angle, which isn't quite what we would be looking for. However, we can be cunning and notice that for very small angles, if you draw the graph of sine and you're only considering small angles, so angles around about here, in fact this is almost like a straight line graph. You can in fact have a straight line graph like this. So for small angles, you can make the very useful approximation that sine of the angle is roughly equal to the angle itself. So this is really great because we can rewrite this as f is equal to minus mg theta. So you might be saying, how small does it have to be? This is if our angle is less than about 15 degrees. So you probably remember when you were in the lab and you found that if you just took a little small displacement to start your pendulum working, it went much better than if you kind of tried to swing it from high up. And that's because these equations don't work if you try to swing it from too high up. But from about 15 degrees or less, then we can approximate sine of theta with the angle itself. Okay, so we know what our force is, but we're actually not interested in the angle, we're interested in the displacement. But we have an equation over here that will tell us about the displacement. So I'm going to substitute theta is equal to, let me get this the right way around, S over L. So I get that my force is equal to minus mg over L times S. And notice that although it doesn't look like what we saw earlier, this is in fact an equation that governs simple harmonic motion, because what we've got over here is a constant. It's just the mass of our little pendulum, which isn't changing, g, which is gravity, it shouldn't be changing, and L, which is the length that we picked. So this is a constant. So we've just described a situation that must be modeled by simple harmonic motion, because we've got a force that is equal to some constant times the distance that you are from equilibrium. So equilibrium is over here, and S moves on either side of equilibrium. Okay, so that's great. We've now basically got something that looks like our mass spring. The only thing that's changed is the coefficient that we have. So since we have simple harmonic motion, we know how to solve this. We know that our force by Newton's second law is always, F is always equal to ma. So we can equate those two, and we have ma is equal to minus mg over ls. Getting rid of our m's, we've got d squared s by dt squared. Just putting my acceleration into terms so that we know exactly which units we're using and which we're using displacement here, minus g over L times S. And at this point you can look at it straight away and say, okay, this part, my g over L, is acting like my k over m in the previous example. So we have the solution just like we did before. That our displacement is some constant times the sine of g over L times t. Whoops. So previously we had an omega over here, but that was because we defined omega to be, I think, k over m or m over k. But in our situation over here, now we've got something slightly different. We've got our g over L, but that doesn't matter. We can still use the same technique. So if this is feeling a bit weird, go back, see how we solved the previous one, and you can see how we solved this one. Now, when you were in the lab, you didn't have an equation that included this. And basically we're going to assume that at time t equals 0, you're going to start from phi equals 0. So you don't have an initial displacement. And so you end up with the thing that you were working with in the lab, which is something like this. Okay, how do we get to figuring out the period relating to this? Well, remember that our omega in this case is going to be g over L. And so we can work out that our frequency is 1 over 2 pi times our angular frequency. And then we know that our period is 1 over our frequency, so we've got that our period is equal to 2 pi L over g. So this is the equation that you were using when you were in the lab, which helped you calculate the value of g if you know the period and the length of your pendulum. All right, so that probably seemed like quite a lot, but there's a lot going on here that I think is useful, particularly in the 6th week of this course, because it pulls together everything you've been doing. So we talked all about, where's my pendulum? Here's my pendulum. So the first thing that you had to think about was thinking about classical mechanics, the force law, how we can work with that to build up an equation for the force. Then we talked about Newton's second law, and we said, well, okay, the only force that we have acting on this is this component here, so that must mean that our acceleration is entirely governed by the gravitational force in the form that we found. So that was a whole lot of classical mechanics. Then we pulled this together into a differential equation. Then we used what we did today, which was solving differential equations, and finally ending up with this equation over here, which tells us how the period changes depending on the length of the string in a pendulum. All right. So here's turning this round a little bit. You can think about how if you were on a planet and you didn't know what the gravity was, if you knew the length of a pendulum and you saw how long it took to oscillate, you could work out the gravity. So here's something for you to try. Imagine we've got a pendulum of 0.25 meters and it swings once every 3 seconds. What is the local gravity? Take a moment to figure that out. Okay, so hopefully you paused the video and you figured it out. So we need to do a little bit of reworking. So we know that T is equal to 2 pi L over G. So if you rearrange stuff, then you should get that G is equal to L times 2 pi over T squared. And if you plug in your the numbers that we've got here, we've got a 0.25 times 2 pi divided by 3 all squared, and if we do that, it gives us about 1.0967 meters per second squared. So the planet where this is the case is a planet which has very low gravity, because we know that our Earth gravity is around 9.8 meters per second squared. Okay. So where do we go from here with simple harmonic motion? It still seems like it's a very simple thing, and you're probably not going to be trundling around to different planets trying to figure out the gravity. So what could we do with this? Well, it turns out that actually we can do a huge amount. So as mentioned a little while ago in this year, you might have heard about a skyscraper that started swaying and people had to leave. Well, in fact, simple harmonic motion and the extensions of it are used to design skyscrapers and mechanisms so that they don't sway. So for example, Taipei 101, which looks kind of like this, is a very tall skyscraper in Taiwan, 1,667 feet, and that can have quite a lot of sway up at the top if it gets pushed by wind, an earthquake, possibly a tsunami. So what did they do? Well, essentially what they did was they hung a pendulum at the very top of Taipei 101. And the idea is that when the building sways, the pendulum sways in the opposite direction and kind of pulls the building back, so that eventually you get a damping motion happening and the building sways. It does sway a little bit, but it is much slower and much more controlled, and it doesn't get out of control. So you can actually build up a simple model of this that you should see this starts looking similar. We've got a spring here on the ground, and here we're thinking of this as the building itself, and then we've got another little spring, and this is the mass of the pendulum. And we can build up the mathematics of this, which is what they did. It looks a little bit hairy, but don't worry, you can see some of the similarities with the stuff that we've been doing. So this equation over here is really the equation that is governing the motion of the building itself, and this second equation over here is the equation that's governing the motion of the pendulum. And you solve them together, and the idea is when you solve them together, because you know a lot about the motion of the building, you can figure out exactly what your pendulum should look like to make sure that in fact your building doesn't do mad swaying. So you tune your pendulum so that your building gets the kind of minimal sway that it possibly can. And if you have a look at this equation up here, it's got some of the things that we've already seen before. So if it just had this term over here, then it would be the simple harmonic motion that we're used to. So it would just be swaying harmonically, as you would expect. But what you want to do is damp that down. So you add a second, so you're adding your pendulum. So that will also impact on the motion. So that's thinking about when you've got your pendulum and your building are in slightly different places, that's also going to impact a little bit on how the building sways. But then the important thing that you have over here is a term which is really called the damping term. And this says that the faster because we've got velocities over here, you look at how fast the pendulum and the building itself are swaying, and you have a term which is also going to decrease the overall motion based on that, and that's the damping term. And then the final term that you have over here, which we didn't see before, is the term which basically is adding the driving force of the wind and things like that. So this force over here is the driving force. So all you're really doing, and this is a very hasty introduction, but I hope you can see, is you're including all the different things that act on the building in order to make it sway. So you've got gravity itself, which is happening over here. Because you've added another pendulum, you've got this term over here. This term over here is based on the velocity of the building itself and the pendulum. And then finally, you've got the force by the wind. You can do the same thing for the pendulum. So you can think through what each of those terms is over there. And then basically by solving these two equations together, you can get the optimal way of building the pendulum to dampen the vibrations in your building. There's plenty on the internet about it, but it's pretty cool. Okay, so that's looking at just single things that are oscillating. But what about if we have a whole bunch of things that are oscillating in the same medium? Well, you know all about this, really. You've been to the sea, you've seen sea waves, you've been studying electromagnetism. Essentially, if we have multiple particles or quantities that are oscillating, then we can get waves. So a sort of formal definition, a wave is a moving oscillation of one or more quantities, usually accompanied by a transfer of energy. So that sounds kind of convoluted, but really what we're just saying is that we have many things that are oscillating in a way that is kind of coherent and transfers energy. One important thing to notice is that waves transfer energy or possibly momentum or information, but they don't transfer particles in the medium. Let's have a look at what I'm talking about here. Well, we've got two basic kinds of waves, transverse waves and longitudinal waves. A slinky spring is a good way to see either of them. So if you have a look at what's happening in our top version over here, our transverse wave, if you imagine any particular particle in our slinky spring, in our transverse wave, it's only ever going to go up and down. It doesn't go side to side. It doesn't move along the wave. It just bounces up and down. So there's a transfer of kind of, you can think of it as energy, which is the kind of wave packet that moves along, but the particles themselves just stay in the same place. And in fact, the same thing happens if you look at a longitudinal wave over here. If you think about what's happening to any individual particle in there, it's just moving backwards and forwards a little bit. It's just that the disturbance is propagating down the wave. So that's what so the kind of important thing to think about is it's not the particles themselves that are moving in a long direction. They're oscillating, but the disturbance is moving. Okay, what are some of the types of waves that we can have? Well, we can have mechanical waves. So those are the things like the slinky spring that we just saw. So waves on a string. If you think about sound waves, so these are waves that are making particles in the air move. We've got water waves, seismic waves. These are all kind of mechanical, actual physical things that are moving, either transversely for a transverse or longitudinally. We can also have electromagnetic waves. So you've done a little bit of that this semester. And we can divide those up depending on the frequency. So we've got radio waves or radon, quite low frequency, all the way up to X-rays and beyond. So those electromagnetic waves are not really particles that are moving. It's more a movement of electric and magnetic fields in a sinusoidal way. But you still have the same sort of thing happening. There are other kinds of waves, gravitational waves, a big thing in Maastricht at the moment because we've got the gravitational wave detector being built. So if you want to learn about those, keep doing physics, and here's a good place to be. There are plasma waves, reaction diffusion waves, bunches of different things, all described using waves. And the equations for waves come a lot from the basics of simple harmonic motion. So just to go into that in a little bit more detail, we've already seen that a differential equation described simple harmonic motion, and then some slightly more complicated differential equations were used to describe our type A 101. So what do the differential equations look like if we want to talk about waves? Well, over here I've got a slightly moved image here. So let's think about the simplest example. We're imagining we've got a string and we're just going to go thunk and make it vibrate. How would we describe that mathematically? Well, if you think about it, we need to consider what's happening at each x value. So we need to be thinking about our string, and we need to, at some particular time, it might look like this. So we need to know what's happening at each x value, and that's happening at a particular time. So we need to consider each x value at some time t. So any description that we have is going to describe our y value. So the height that we've moved away from equilibrium is going to be a function of where we're looking and when we're looking. So we really have two variables that we need to consider. We need to consider the x value and the time. So we're not going to go into the details of this, I'm sure you'll be glad to know, but you can actually analyze it using Newton's second law, just like we've been doing, tension, forces and stuff. So you can look at your string. So here we've got our string sitting like this, and you can analyze it in a little bit more detail here. So we know that we've got a certain mass of the spring, it's got tension in that direction, tension in that direction. We know that it's got gravity acting down here, so this little mg there. So you can put together your force diagram, and then using your F equals ma, so you model the force based on this, and then you make the equation F equals ma, and overall what you end up with is an equation that looks like this. So this probably looks quite different from what we saw previously if you look at it closely. So it has a dy by dt squared, so that's kind of what we would expect. That's the acceleration part. So this is our acceleration. It's got a term over here which involves the tension, and mu, which is, I think, the mass density. But what is slightly different over here is this has the second derivative of y with respect to x, not with respect to t. So this is talking about how the position in y is changing depending on where you are in x. So this is so an equation like this is a differential equation, and it's called a partial differential equation because it has two different kinds of derivatives. It has different derivatives with respect to time and with respect to displacement. But just like there are plenty of techniques for solving ordinary differential equations, like we saw earlier, there are techniques for solving things like this. And if you get the solution, it looks like this, which might look a little hairy initially. But there are some key features to take out. So let's have a look at this because it's kind of helpful. So what have we got? We're saying that at any time t, the displacement of our string, so remember we are thinking about a string that is oscillating, is determined by this crazy equation over here, and it depends on where we're looking and when we're looking. So the first thing is that this is an infinite sum. So we've got a whole bunch of terms. So we can think of this as, for example, a1 cos of nu pi t over L sine of pi of x over L plus a2, and you're going to have a whole bunch of terms. Usually with physical things, it turns out that the amplitude of this first term is going to be really big and the rest are really small. So mostly we get to ignore the rest of the terms over there. So we're really just looking at something like this. And now if you look at this, this should start to look a little bit more sensible. What have we got? We've got some amplitude, which is kind of what you would expect, times, well, this term over here is giving my time dependence. And if you think about an oscillating spring, it oscillates sinusoidally. So you would expect that over time you would have some sinusoidal vibration. And similarly, this term over here gives my spatial dependence. And again, if you think back to this image that we have over here, if you look at this spatially, we've got a sinusoid over space. So in time, looking at a particular point, for example here, we're seeing that it's oscillating up and down in time, but in space we also have that it's oscillating in space. So for a kind of hand-wavy explanation, this shouldn't seem too surprising that in our final solution we have a term that oscillates in time and oscillates in space. Phew. Okay, don't worry, you don't have to know that. I just wanted you to get a feel for where you would go if you're carrying on in physics. Yeah. So in summary, what have we done? Well, we talked about vibrations, because pretty much everything can vibrate, and we firmed that up into a definition of oscillations. And then we said, okay, let's take the simplest possible system we can and describe that mathematically. So we developed simple harmonic motion. And after we developed simple harmonic motion, we used that idea to talk about things like pendulums, and then extend that to things like helping buildings not sway. Then we went a step further and we said, okay, suppose you have a whole bunch of oscillating things, well then you can end up with waves. And we talked a little bit about how you might use mathematics to describe waves. What are the things that you need to know? So the key thing to take out of this is that a differential equation that describes simple harmonic motion looks like this. Now you might not have an explicit omega squared, so if you think about when we had a pendulum, we ended up with a differential equation that had a g over L, and previously when we talked about our mass spring we had something else. But usually what you do when you have a system that looks like this is whatever you have as your coefficient of your displacement here, you're going to turn it into your omega squared. So you're going to equate whatever crazy coefficient you have here with omega squared, because that's going to tell you your angular frequency. And that's useful because when you're in this form over here, the solution is this bunny over here with your angular frequency over here. So you can always find, given your coefficient in whatever system you have, by translating it into omega squared, you can find your angular frequency. And what's useful about that is because your coefficient comes from the physical system. So when we had the mass spring, we saw that it was the spring constant and the mass. When we were looking at the pendulum, we saw that it was the length and the gravity. You can tell that your angular frequency is it's a natural thing that happens from the particular system you're looking at and is determined by the system. So in the mass spring, your angular frequency is determined by the spring constant, so how stiff the spring is, and by the mass that you're using. which kind of makes sense because remember, angular frequency is a measure of how fast it's moving. When we're thinking about the pendulum, our angular frequency is determined both by the length of the pendulum and also by gravity, which kind of makes sense. Okay. All right, so you need to know how to solve this differential equation. And by solve, I mean figure out that you need a sine wave and how to find your omega. You also need to be able to convert between our normal frequency, so cycles per second, and our period and our angular frequency. Okay, and just because it might turn out to be useful for this course, and it gives you something, it gives us examples to work with, be able to understand how we got to this equation and how you can use this when you're talking about a pendulum for small oscillations. So the link between the period of the oscillations, the length of the pendulum, and gravity. Other than that, what do you need to know from this lecture? You need to have a broad idea of some of the things that can be described using oscillations or waves, and have a bit of an idea of the difference between transverse and longitudinal waves. And that's about it. I hope that I will see you in future physics courses or possibly maths courses. I do in fact teach the differential equations course, so yeah, if you come join me in that course, we'll talk a lot more about vibrations and waves.